Okay, we're going to talk a little bit about effective nuclear charge. Okay, and the trend that goes along with it. Okay, effective nuclear charge is basically the level of attraction that the nucleus has for the outer electrons. Okay, so if you had an atom, if I was going to draw an atom, let me pick red. Okay, if I have a little atom, okay, here's its nucleus, and let's say that this nucleus has, I'm just guessing here, 47 protons. And around here we have 47 electrons. Okay, very rudimentary diagram. And let's say I was going to analyze this electron right there. Okay, this itsy bitsy electron. Okay, the effective nuclear charge would be the attraction that the nucleus has for this itsy bitsy electron. Okay, 47 protons. Okay, in this soup. Okay, and the soup would be the 1s2, the 2s2, the 2p6 onward. Okay, in the electron cloud, there's 47 electrons. In the nucleus, there's 47 protons. So it's a 1-to-1 ratio. But the attraction level for the electrons is not the same. Okay, remember that we have shells. Okay, shells are kind of like layers to the onion. We have electron shells at play. So if we have our 47 electrons, we have the 1s, okay, the 1s, the 2s, the 2p, the 3s, the 3p, and some in the third, okay, and here's the fourth. Starts to look like a bullseye. Okay, this is the 4s and the 4p and the 3d. Okay, we're going to call it the 4s. This electron, okay, and there's going to be 8 here. And it's not really 8, but who's counting? This itsy bitsy electron, okay, in the exterior is not as attracted to, okay, the nucleus. We'll do the nucleus in blue. All right, so when I'm isolating to look at this electron and the nucleus, and I'm looking at the attraction difference, it's definitely not as strong as the attraction of the inner electrons to the nucleus. Okay, there's actually quite the difference. And you have to think of the reason why. It's a 1-to-1 ratio, but we said the positivity, I remember this in class, we said the positivity of the nucleus is already being used up or shielded by the other electrons. Okay, what I'm saying is that yes, we do have quite a few protons in the middle, but their pull on the outermost electrons is not as great because they're pulling out all the other electrons underneath. Okay, they're being shielded or insulated. The electron is being shielded or insulated from the proton charge, okay, or nuclear charge. Another way of looking at it is that there's an attraction here, but what about these experiences? Okay, electron to electron experiences, okay, the forces that are being had here are going to be repulsion. So not only are we do have a light attraction to the nucleus, but we're also being repelled by all of the other electrons. Okay, so that's the whole concept of shielding, that your outermost electrons are growing less and less attracted to the nucleus because of this whole concept of all the other electrons in the way, all the other shells of electrons. So the trend is, as we go down the periodic table, effective nuclear charge decreases. Okay, and again, the reason was that as you go down, you add energy levels or shells. Okay, you're adding orbitals, layers to the onion, and all of the other electrons shield the outermost electrons from the nucleus. Okay, and there's a lot of other things you can go a lot of other directions, but that's sufficient Now, as we go across a period or a row, okay, we have to talk about effective nuclear charge there. Now, this is a different scenario entirely, because as we go across a row, as we go across a row, okay, we're not adding any energy levels or shells. Okay, what are we adding as we go from H to HE, or better yet, we might want to take lithium, beryllium, the second row. Lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. As we go through that row, we're adding both a proton and an electron. Okay, we're going to ignore neutrons for right now. We're adding a proton and an electron at every click of the way, every tile of the table. And we're not adding any extra energy levels. We did that when we were going down. We added extra energy levels as we went down the column. Now we're going across a row. We're not adding any extra layers, any extra shells. So the effective nuclear charge, or the attraction, actually increases. Okay? And it increases because we are increasing the negative and positive forces at play here. Okay, because the number of protons, which are positive, and the number of electrons are going up, we are experiencing more attraction. Okay, so attraction actually goes up or increases as you go across a row. Okay, the reason why that didn't apply on the downward is, yeah, we are adding a bunch of electrons, a bunch of protons every click. I mean, look at, from going to 19 potassium to rubidium, you're adding almost 20 electrons and protons. Okay, right? We're adding about 18 protons and electrons. We're adding quite a few protons and electrons, but we're adding also a bunch of another layer to the onion. All those electrons are actually in between the outermost electron. As that's not a factor whatsoever. The factor of adding extra levels does not apply as we go across a row. So now we have the tendency of making the proton stronger because we're adding more, or the proton force increasing because we're adding more protons. And we're making the negative force also stronger because we're adding electrons. Okay, and attraction will actually go up. It's almost like two magnets getting somewhat stronger, okay, but keeping basically the same distance away from each other. Okay, attraction goes up as we go across a row. Attraction decreases. Okay, and again, attraction of what? The outermost electrons decreases as we go down a column. That's effective nuclear charge. Okay, we're talking about, again, to define it, the attraction that the outermost electrons experience or get from the protons in the nucleus. All right. Now, that was the trend for effective nuclear charge. I'm going to very, very rapidly go through the other trends. Okay, and I'm not going to really write much. I'll just talk and write the arrows. Okay, try to do this as quick as possible. Okay, we had another one, atomic radius. Okay, I'm just going to call it AR. Well, atomic radius is increasing as we go down the columns. Okay, so the size of the atom gets larger as you go down one of the columns. And the reasoning was because of shielding, effective nuclear charge or attraction decreased. And without the attraction, without as much attraction, the electron shells or orbitals kind of plump up or expand. Okay, I mean, it just makes sense. They're not held as tightly, so they're going to expand outward a little bit. Okay, so atomic radius increases as we go across. I'm sorry, down. As we go across, it decreases. Okay, so the size of the atom actually decreases as we go across. Why? Attraction or effective nuclear charge goes up. Okay, when that occurs, the electrons are contracted or pulled inward. Okay, since there's more attraction, there's electrons are being pulled more towards the center. All of these trends work really well when you're thinking of the center of the universe, or the center of the system that you're studying being the nucleus. Okay, it's the nucleus that's dictating the terms because it's right there in the center and everything's revolving around that. So I'm going to say that one more time. Again, keep in mind that the nucleus is who's dictating what's actually happening. So the nucleus is, the effective nuclear charge is increasing, so attraction is increasing. So the nucleus of the atom with all the protons inside is pulling the electrons inward. Okay, so that's atomic radius. Okay, I believe next on the agenda was ionization energy. Okay, and ionization energy was the energy required to remove. Okay, energy required to remove an electron. And it increases and also decreases. It's the opposite. Okay, so I'm talking about ionization energy, energy required to remove an electron. Now, again, I'm actually going to go faster and faster because it's always the same thing over and over again. Attraction, as we go across the periodic table, is increasing. Effective nuclear charge is increasing. So that means there's more attraction. It's harder to pluck an electron away. So ionization energy goes up. That makes perfect sense. It also makes complete sense as you go down one of the columns. Effective nuclear charge decreases, i.e., or which means that it's easier to pluck an electron away. Less attraction, there's less force holding the electron to the nucleus, so it's easier to remove an electron. That one's not so bad. Okay. Next on the agenda, I believe, was electronegativity. All right, so electronegativity, okay, again, looks like this. And electronegativity, electronegativity, I'll just spell it. Electronegativity was the general attractiveness, okay, it's a level of attraction an atom has for additional electrons. Okay, so we're a neutral atom, and now electronegativity takes into account the level of attraction the atom has for getting another additional electron or electrons. Okay, and just like ionization energy, it's an ID. And for the same reasons, because they're all the same. When you're going across a row, attraction increases. Not only are you very attracted and you attract your electrons, in fact, so much so that the atoms constrict and get smaller. Not only are you very attracted to your own electrons, you could also attract additional electrons. So the electronegativity value is high. Okay. As you go down the columns, or any column, electronegativity is decreasing. Why? Effective nuclear charge is decreasing, so there's less attraction. Less attraction, okay, due to shielding, less attraction means that I'm not going to be able to attract, if I'm an atom, I'm not going to be able to attract an additional electron. I'm having a difficult time holding on to my own electrons. So I'm definitely not going to attract any more electrons. So electronegativity going downward is decreasing. Okay. The last one was ionic size or ionic radius. Okay, ionic radius. And if I put my staircase in here, okay, remember the staircase separated the metals, okay, over here, metals, that's supposed to be an S, metals and non-metals. Okay, the only exception is H is a non-metal. And you must know that the metals, they tend to form positive ions. And the nonmetals tend to form negative ions. Okay, they don't have to be an ion, but when they're an ion, This side of the left side of the periodic table, the metals tend to form positives, the right side negatives. Okay, let's just talk about that. When you're a metal and you form a metal ion, which is a positive ion or cation, what happens to the size? Okay, what I'm talking about is, let's do lithium here. My little lithium has 3 protons and, okay, I'm just going to put these together, dot, 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 3 electrons. If I was going to make this lithium ion, which forms a +1 charge, a lithium with a plus charge, what do you think happens to the size or the radius? It constricts. Okay, that makes, again, perfect sense. Why? Now we have 2 E's, lithium +1. We have 2 E's that have a negative charge, and we have 3 P's that have a positive charge. Okay, remember I said the perspective, the nucleus is the center, that's the guiding force. So the nucleus is pulling the electrons inward. Okay, so we get to constrict. Attraction is going through the roof. You have 3 P's pulling on 2 E's, so they're more attracted. So first things first, you have to know that the plus ions are smaller than their counterpart, okay, compared to the neutral atom. The opposite's true over here. Okay, if I had F, okay, F has 9 electrons and 9 protons. If I was going to make it 9 electrons and dot, 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 okay, that's probably 9. 9 electrons. If I was going to add an additional electron, so 1 extra electron goes into the mix. If I was going to add an extra electron, now what do I have? I have a situation where it's skewed, where now my 9, and I'm sorry, I drew an E, this should be a P. Now I have my 9 protons in the center trying to pull on, okay, the exterior with my 10. Okay, when I add this one, it goes up to 10 E's. All right, and I actually don't like this picture. I want to do the fluorine over here. So now I have 9 electrons with 10. And let me get down because I think I just said that wrong. Now I have my 9 protons in the center. Okay, with now 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. With 10 electrons. Okay, that's a very rudimentary picture. Okay, it's a very rudimentary sketch. I have 9 protons and 10 electrons. Well, compared to being 9 and 9, now it's 9 and 10. We have an extra electron because we're dealing with, okay, what are we dealing with? We're dealing with fluorine, which now has a charge. It's called fluoride now. It's not just fluorine. It's F minus 1. I added an electron. Which one? One of these 10. It was added. It's not 9 and 9. It's 9 and 10. So now we have an extra electron. And we're not going to get smaller as an atom or as an ion. We're going to get larger because now we have 9 protons tugging at 10 electrons instead of 9. Okay, so traction isn't as large. Okay, traction goes down and the ion is now bigger than its counterpart, the neutral atom. Okay, so before we even get to ionization, before we get to ion radius, we have to know that positive ions shrink, negative ions plump up. Okay, so now we're going to do ionic radius. I call it IR, ionic radius. And just like atomic radius, we're decreasing and increasing. And for the same reasons. The same reasons as all the other trends. Why? Because attraction increases as you go across. Because you're adding both protons and electrons without adding any extra energy levels or shells. So attraction increases, so the size decreases. And again, going down, the reason was because of shielding. Attraction goes down, and the electrons are free to move a little bit, and they can expand. So the radius of an ion increases as you go down. The only difference between the two, atomic radius and ionic radius, is that it resets at the staircase. Okay, what I mean by that is we might have a situation where we have, I'm just going to draw some balls here. So we have something like this. They're getting smaller as we go. This one plumps way up because now we're at a negative and it resets. That's what I mean by it resets. The general trend is decreasing as we go across, but it resets at the staircase. Okay. Increasing as we go downward. What I mean by that is I might have something like this. And then it goes way down again. And then it starts to increase again. Okay, so we can see that we started off small, got larger, larger, kind of reset. Okay, I'm going to draw this one just a touch bigger. Kind of reset and then got larger again. Okay, I might have went a little too far in my bismuth. Okay. Or not far enough, I should say. A little bit bigger. Okay. So as I went down, it went increasing, increasing, increasing. When I hit the staircase, it resets, so I get smaller again. Okay, and let's draw this for antimony just a little bit smaller, just to show the trend. Okay, this isn't to scale. So increasing, increasing, resets. Go back. What I mean by resets, goes back to small, increasing, and if I had another theoretical atom here, okay, which we have the 3-letter designation, I don't have this one memorized. This one would be increasing again. As we go across, we're getting smaller, we're getting smaller, we're getting smaller, plumps back up again, and then we're getting smaller, we're getting smaller, we're getting smaller. Okay. All of these trends are relatively, they're just a trend. They're not an absolute rule. So don't think that they're always set in stone. But as a general trend, as in a majority of the atoms and elements and ions follow the rules, that's true. But as a hard, fast rule, okay, that's absolute, it's not that. It's not the law of the land. But it does give us a better idea and a better picture of what's going on in these atoms and some of the attributes they have.